You know, every single thought you have, every move you make, every sensation you feel, it all runs on electricity. Now, not the kind that's in your walls, but a really special biological spark, a tiny electrical signal that zips through your entire nervous system. So let's dive right in and explore the fundamental signal that powers our minds, the action potential.
So take a look at this. What you're seeing here is a synapse. It's the microscopic gap where two nerve cells meet and talk to each other. I mean, it looks incredibly complex, right? And it is. But the communication happening here really boils down to a simple, elegant electrical event. This is literally the stage where the drama of your mind unfolds.
Okay, so that brings us to the big question. A nerve cell, a neuron, can be incredibly long. I mean, some of them stretch all the way from your spine down to your big toe. So how on earth does it send a message that entire distance without the signal just fading away?
Well, the answer is pretty cool. It lies in the neuron's surprisingly rich electrical vocabulary. It's not just a simple on or off switch. Nope, neurons use different kinds of signals for different jobs.
Think of it like this, right? Receptor potentials are kind of like the first little whisper of a sensation, like someone tapping your shoulder. Synaptic potentials, that's the quiet, graded back and forth conversation happening between neurons that are right next to each other. But the action potential? Oh, that's the long-distance shout. It's the high-fidelity, all-or-nothing signal that's designed to go the distance. It's the one that can't be ignored.
And this is the real challenge we're talking about. The axon, that's the long cable part of the neuron, is actually a terrible electrical conductor on its own. I mean, if you just injected a little bit of current, it would fizzle out in just a few millimeters. So how did biology solve this huge engineering problem?
And this slide just illustrates the solution so perfectly. Look at the graph on the left. That shows what happens to a simple electrical signal. See how that wave just shrinks and shrinks as it travels? It just gets too weak, too fast. But now, look to the right. That's the action potential. Notice how this signal maintains its full height, its full strength, all the way down the axon. It's a self-regenerating wave of electricity. It is biology's very own booster system.
So how does the neuron pull this off? How does it generate this special signal? Well, first things first, it has to charge its battery. It needs to build up an electrical potential across its membrane, just getting ready and waiting to fire.
And this is all made possible by two key types of proteins. On the left, you've got active transporters. You can think of these as these tiny, hard-working pumps. They're constantly pushing ions to where they don't naturally want to go, and that creates a really steep chemical gradient. Then on the right, you have ion channels. These are the gates, and when they open, they let those ions rush right back down that gradient, releasing all that stored energy.
And just get a load of the imbalance those transporters create. This table shows a huge amount of potassium packed inside the neuron and a massive amount of sodium waiting outside. This difference in concentration and the charge that comes with it, well, that's the neuron's battery. It's all just stored potential energy, waiting to be unleashed.
Now, all of this leads to a really crucial concept, electrochemical equilibrium. You've got two forces fighting each other here. First, there's a chemical force. The ions want to spread out, to move from high concentration to low. But as these positively charged ions start to move, they create a second, opposing electrical force that starts to pull them back. So, equilibrium? That's the perfect balancing point where the chemical push is exactly canceled out by the electrical pull. Nothing else moves. Okay, so let's see how this actually builds the neuron's resting state. When a neuron is just sitting there, quietly waiting for a signal, there is one particular ion that is the undisputed star of the show.
And that ion is potassium. See, at rest, the neuron's membrane has all these little channels that are open, but they're mostly just permeable to potassium. And since there's way more potassium inside the cell, what do you think it's going to do? It flows out, right? And it takes its positive charge with it.
This classic experiment by Hodgkin and Katz is the absolute smoking gun. What they did was they changed the amount of potassium outside a neuron. That's the x-axis on this graph. And then they measured the internal voltage, which is the y-axis. As you can see, the data points form an almost perfectly straight line. The neuron's resting voltage is directly tied to the potassium gradient. This proved it. It's beautiful. And this quote from the source text just sums it all up perfectly. The negative resting charge of about -65 millivolts exists for two simple reasons. The membrane is leaky to positive potassium ions, and there's a ton of them inside just trying to get out.
But what happens when the neuron decides it's time to fire?
everything changes. The story completely flips. The neuron gets inputs, its voltage starts to drift up towards this critical tipping point, this threshold, and when it crosses that point, we go from the quiet tale of potassium to the explosive drama of a totally different ion.
Once that threshold is crossed, it's an all-or-nothing event. For just a millisecond, the neuron's membrane undergoes this radical transformation. It suddenly becomes incredibly permeable to sodium. All those sodium channels that were closed before, they fly open.
And here's the proof for sodium's starring role. Hodgkin and Katz did the same type of experiment, but this time they messed with the external sodium concentration. And just look at what happened. The resting potential, that baseline voltage on the graph, it barely changes. But the peak height of the action potential, that really sharp spike, it's directly tied to the amount of sodium outside the cell. It is a sodium story, through and through.
So, at the end of the day, it all comes down to this simple, beautiful duality. The resting state is the potassium story. You've got K+ flowing out to create a negative charged battery. But the action potential, that's the sodium story, with Na+ rushing in to create a powerful positive spark.
Now, this isn't just abstract science locked away in a lab. Understanding this electrical code actually allows us to hack it, to manipulate it, with some incredibly important real-world results.
So think about it. We know that the spark, that action potential that carries a pain signal, for instance, is caused by sodium channels flying open. So, what happens if we can just block those channels?
This is exactly how your dentist numbs your mouth. Local anesthetics, like lidocaine, are really just sodium channel blockers. They physically get in there and plug up the sodium channels. So when a pain stimulus arrives, the neurons simply can't fire an action potential. The pain signal is stopped dead in its tracks before it even really begins.
It's honestly incredible to think about. This simple spark, this little dance between potassium and sodium, is repeated billions of times a second across the huge network of your brain. And it's the basis for everything you are. It really makes you wonder what complex thought, what brilliant idea is being built from these simple sparks in your own mind right this very second.